Let me introduce Dr. Ciprian Catana, who is a guest speaker here. So Dr. Catana received the MD degree from University of Medicine and Pharmacy, Tagul, I don't know, did I correct? Romania. He subsequently conducted a PhD research in biomedical engineering at UC Davis and a postdoctoral training at MD. And he's currently a professor of radiology at Harvard Medical School and then director of integrated PET MRI imaging at the Martinos Center, which is big research center at MGH and at Harvard Medical School. And the director of collaborative research and innovation molecular imaging. He's also a vice president of a physics, instrumental and data science council, and an immediate past president of Brain Imaging Council, and an elected member of the board of directors of the Society of Nuclear Medicine Molecular Imaging. And Dr. Catana is also ad hoc reviewer for numerous national, international funding agencies, and currently permanent member of NIH Clinical Translational Imaging Science, CTIS, study section, and also active scientist and expertise in PET imaging research method, technology development, and the application in neuroscience, cancer, cardiovascular imaging, and lung disease. So it's not just the brain, but the whole body. And he leads a national recognized research program funded by full NIH grant and an industry sponsored the project, and a focus on multimodal simultaneous PET MRI imaging technology and application for these tools to study various patient populations. While MGH, Dr. Catana has directed and guided over 30 trainees in this field and currently contacted PI for T32 grant, a postgraduate training program in medical imaging. And he is at the personal level, he's an avid skier. So when I approached to him would you want to come over for grand speaker like last February or March in PCR, right, Vienna? He's like, I'm gonna come winter. So you really find that it happened in January, and in fact, his flight get there on time. Despite all the weather going on in this country, he already skied yesterday because the hotel room wasn't ready. So he popped out and went to ski. So there's a good reason for him to be here, but it's really grateful to have Dr. Catana for incredible expertise and a PET MRI and also 7T MRI because Martinos Center has everything you can imagine. So he'll be speaking about evolution of human brain PET imaging at the Martinos Center, from MRI integration to high sensitivity. Thank you so much.
Thank you very much. With all those titles, when do I have time for skiing? But this is how I do it. I actually went skiing in Austria as well, right after.
Austria.
Good. My pleasure to be here today. Disclosure relevant to this talk, Siemens and United Imaging. So for those of you who are not familiar with the Martinos Center, you said it's a big research center. I think it's the biggest research center at MGH. It started many years ago, many years before I joined in the 80s as the NMR Center. And there are a few things that we like to take credit for, like the FMRI that in the 90s. Around 2000, we changed the name from the NMR Center to the Martinos. There are a few more thoughts on that timeline, 2008, 2011. I'll tell you about those. Currently, there are about 120 at the whole Martinos Center. And there are many other investigators for the center and resources. And in terms of resources, we have 8 human brains, or Bay 1 to Bay 8, where we house our MR scanners, currently all Siemens scanners. We have 6 3Ts, 2 7Ts, although that kind of changes every month. There is some change. We have Malaysian energy, optics, TMS, small animal facilities. In terms of our location, we are part of the radiology department at MGH. We are located with the main MGH campuses, but Yeah, because maybe I will be on nine. This here in the corner of the MGH is across the first figure is see here, but over there, and then in the other on the diagonal, in the other side of that map is where the longer medical area is located. I joined the Martinos Center January 2007. I actually went back last night to see when I defended. 1 week after I defended, I moved to Boston. And on the 13th, 13th or 16th, I don't remember. Anyway, of January, and then I moved to Boston. So that was January 2007. And when I arrived at the Martinos Center, there were not 8 bays, but 6 bays. And one thing I noticed is that there was no PET scanner installed at the Martinos Center at that time. The other thing I will point out is that we had the one GE scanner that was used for clinical purposes exclusively. But other than that, all the other scanners were used on research. In the meantime, the clinical scanner moved and replaced it with another research scanner. So all the studies that are done at Martinos Center, scanners we have available are used 100% research. So I joined the Martinos Center because I knew the first integrated PET MR scanner was going to be installed there. That's the BrainPET prototype developed by Siemens around 2007. We installed ours in May 2008. So for the media, this is how Siemens started in the PET MR field. They put this dedicated brain scanner to be integrated in a Statio scanner, their state-of-the-art Tesla at that time. And we were the first US installation. They built 4 of the scanners. First one always was installed in Germany, then ours, and then there was one in Emory and Germany. I'm going to give you a lot of examples of studies that were scanned. On the right is actually our third patient, which is quite an interesting case of a glioblastoma with the extracranial extension, something like that. In March 2011, we installed the biographer in March. 3 months from the prototype, the prototype that learned from that, and they built this integrated full body the PET mark and the biographer mark. So again, the first US installation, the second one is as well. Started in March. In May, we scanned our first subject. I won't go into a lot of details about the performance characteristics of the scanners. The BrainPET being a dedicated brain scanner has higher spatial resolution, higher sensitivity than the MMR, but obviously the MMR and other body parts, not just brains. I want to point out that very recently a GE PET MR scanner was installed at the main campus. So this is not Martinos Center, but it's run by the nuclear medicine department at MGH. So that happened, I think in October, might be wrong, September, October, they scanned the first patient. This is the latest generation PET MR scanner, time of flight capabilities like Siemens, that GE years ago. All the examples I'm going to present today are from studies performed on the Siemens scanners because those are the scanners we have there. After joining Martinos Center, I've established the integrated PET MR lab, and we have been focusing on either adopting or developing a next generation imaging hardware, implementing methods to use data synergistically, and then in collaboration with many investigators on applying these tools to research and clinical studies in brain, heart, lung, liver, and prostate and all genital. As evident from the title and the way I highlighted this slide, I'm not going to talk about anything below the neck. I will focus only on brain today. Before I do that, I'd like to acknowledge some of the students, postdoctoral fellows, clinical coordinators, junior faculty or faculty now have been part of my lab years. So I showed you the scanners. I mentioned we also develop methods to use the data synergistically. So what do how can MR and PET data be used synergistically? On one hand, the simultaneously acquired MR data can be used for improving the PET data quantification. And I'm going to talk about some corrections. In turn, the temporal correspondence of PET signals might help us better understand a number of people, and in the end, simultaneous PET MR might enable us to obtain improved models. So in terms of those corrections, attenuation correction, I don't know how much you know about the technical parts of PET and methodological development. So for each of the slides, I have a brief introduction of physics. As you know, 511 has been the subject, and we need to account for this, both for qualitative and quantitative analysis. Otherwise, it impacts PET data in various ways, bias quantification, image artifacts, image noise. Well, this correction is particularly challenging in an integrated PET MR scanner for many reasons I won't go into when it comes to the body, but I don't think about the brain. The biggest challenge, especially in those early days, was that we needed to obtain the information needed for performing this correction from the MR data that required, since the scanners don't have a CPU, they can come with the transmissions first. So the biggest challenge when it comes to brain is segmenting the bone from the MR images and separating bone from hair cavities. Now, soft tissue is relatively easy to obtain. For years, we developed several methods to address this challenge, starting from the one on the left, where we used this advanced ultra-short echo time sequences to actually image the bone, where data very short echo time, and you compare that to the data acquired from the normal echo time, you will see, and due to somewhat post-processing, you are able to segment the bone from hair cavity to soft tissue. And that's how we that's how we implemented one first approach for addressing this challenge. Later on, we also incorporated anatomical information that we collect anyway on all patients, and we improved the quality of the attenuation maps. You might notice if you look carefully, and I think you can see it on the screen as well, that this two mu map generation methods generate segmented mu maps, where only a limited number of tissue classes are segmented. Bone, soft tissue. I hear something. I don't know if that's because of me or because of somebody else. The MP range, I don't think I hear it.
That's okay.
Yeah, good. The MP range approach, the last one on the slide, was developed by David Squerdo in my group, and it allowed us to generate what we call pseudo-CT, so CT equivalent attenuation, CT equivalent maps from the MP-RAGE data. And it is the method that we have been using for the majority of our studies over the last decade or so. For both scanners, not just for the brain PET, but also for the MR. This method actually worked better than the method implemented by manufacturer. The other correction I mentioned, or I guess I should call it an opportunity. No, attenuation correction was a challenge. Motion correction is an opportunity, as we know. I mentioned earlier that we do research studies. Well, research studies as opposed to clinical studies take a long time. We often scan our subjects for 90 minutes, sometimes even 120 minutes, and it is impossible for the subject to stay still, so there will be motion. It will obviously have an impact on quantification. The better the spatial resolution scanner, the more motion will have impact the quality. It can introduce attenuation mismatches, bias quantification, and so on. The opportunity in an integrated PET MR scanner is to use the MR information quite simultaneously to track the motion of the head. It applies to other body parts as well. And then, since we recorded data simultaneously, we can apply this motion estimates to the PET data. I'm not suggesting we should use PET MR, the MR scanner as just a motion tracking device, but by level of implementing the sequences, you can obtain the information needed for motion correction in the background of the information for either morphological studies or for. We performed the first proof of concept studies in healthy volunteers who were asked to move their heads several times during the acquisition. And you can appreciate in these images the substantial improvement in quality after motion correction. Still working on this, still trying. This was an FDG example like FDG, but we are implementing this similar methods for very satellite tracing. The third correction addresses another limitation of PET, the fact that spatial resolution is limited and partial volume effects affect quantification. The opportunity in integrated PET-MR scanner is to use, especially if you do motion correction, if you have perfect registered PET and MR data, is to use the morphological, high resolution morphological information provided by MRI to perform this correction. And I'm not going to claim we are the first to develop these methods. Many such methods have been developed over the years. But again, the opportunity when you have perfect data is to do this more like this. Instead of just applying this, using this information post-image reconstruction, we develop methods in collaboration with Gene Chief for incorporating the high-resolution morphological information directly in the reconstruction, as you can see in this example. Kevin Chen, a former student in my lab, developed this pipeline workflow that allows us to do all these corrections I mentioned using data collected with a single MR sequence, the MGH with MDID motion navigators. And using this data, we can generate again attenuation map, we can perform an anatomy-aided reconstruction, we can segment all the regions of interest for data analysis and perform corrections. One theme in my lab was the fact that we didn't just develop these methods for ourselves. We made all these tools available to investigators using our scanners, and even created this automated pipelines for processing the data. And there were many people who contributed to developments over the years. I acknowledge here some of them. And most of the studies that I'm going to discuss later were actually processed using these tools. One thing I didn't mention in the context of the BrainPad when I introduced the BrainPad is that scanner actually, as opposed to pretty much every scanner that you've seen in a clinical setting, it didn't come with a nice graphical user interface and tools for automatically reconstructing the images. No, we're requiring the Lismore data and we're applying all the corrections with the standard corrections, not even the ones I mentioned today, ourselves offline. So investigators who didn't have the expertise to do such things, they relied on these tools for their studies. So let's move into the application. So PET-MRI, as you can appreciate from these tables, they provide complementary information, and the simultaneous acquisition of the data sets enable studying molecular processes together with physiology and functional parameters in the same physiological state and condition. Our PET-MRI scanners are located next to our radiochemistry facility, which was established by Jacob Hoover in 2011. And here are some of the several dozens of radio tracers validated for human use over the last decade or so, including the three at the bottom. Realize now that red maybe is not the perfect color when I show the slide. Change that. First one there is Martinos. That was the first radio tracer we developed with the Martinos Center in the lab, and we took it all the way to humans. And then there are two more developed in Peter Caravan's lab, FBP8 and CBP8. I'm not going to talk about those two today. One is fibrin targeted probe, or the other one is a collagen targeted probe. We do a lot of cool studies with those as well. Maybe if you are interested, I would be happy to come back next year for another winter and talk about whole body applications of PET-MRI. So the scanners, the radio tracers would be useless without investigators interested in using these tools for their specific research and clinical applications. And over the last 15 years or so, we built a community of investigators who, according to our website, so it's not, don't trust, take my word, but according to the information posted on the Martinos Center, if you look at people and you search for area of interest and you write PET, you will get that maybe changed a little bit since the last time I think that's it. But there are a few thousands of investigators who now use PET for one reason or another, their studies. And it would be impossible to talk about all the very interesting studies. Don't try to read performed by my colleagues using PET-MRI. This is one slide, many papers that came out of this, 2010, 2017, 2017, 2020, 2020, 2024. There are still many ongoing studies, both the brain-PET prototype and the MMR. So next year or so, 3 years, I'll have another slide with the using data required of the scanners. And this is incomplete. It's actually hard to I'm not co-author on all those publications. It's actually hard to keep track of all the papers that come out of this. I won't go through all of them, but I will give you a few examples of studies, and I group them into neurological applications, neuropsychiatry, neuroscience. So, and I will kind of go through the evolution of this from the early days. I mentioned on that slide when I showed the brain-PET that we started with brain tumor patients. That was at the time in 2008 when we installed the brain-PET. We didn't have a cyclotron. As I mentioned, our radiochemistry was, fertility was of 2011. So from 2008 to 2011, we had to rely on other radio tracers that we purchased from outside. FDG, we started with FDG. Actually, my first R1 was just FDG. So interaction of patients, a lot of methodological developments, then general migrants are two aims that are methodological developments, and the third one that's applications. Maybe now we have more and get it. So in this case, we started with FDG, not that exciting, but again, it allowed us to get started with the novel imaging modality. We then moved on to hypoxia for cellular proliferation. Quite interesting once we had the cyclotron side. We, Jacob's first group, they developed a method, a more efficient method to label temozolomide, so the standard agent in this patient population. And it was at the time when we were doing a lot of studies in this patient population using anti-angiogenic agents, studying and concepts that take me back to my early days at the Martinos Center. And when you have, and this is an example of such a study where temozolomide, we image these patients with radio-labeled temozolomide before and after the start of anti-angiogenic therapy. Also in the neurological category, one of our most successful programs was built around PBR28, which binds to the inflammatory marker transcription protein. We started with chronic pain, Marcologia. He started as a postdoc, now he's associate professor, and so many grants on different other aspects, but I have just one portion of a slide that I'm going to talk about. Okay. So in this case, we observe neuroinflammation in the thalamus in chronic patients. Quite interesting when you look at all the subjects in the group level map, but when you look at the subject and control, you see similar differences between on the subject level, which is quite amazing. We also used it in other patient populations. We showing neuroinflammation of the basal ganglia in Huntington disease, in the cortex, cortical lesions, deep gray matter, and normal appearing white matter in multiple sclerosis, in the motor cortex in ALS. And on the contrary, individuals with ASD exhibited lower TSPO expression in several brain regions shown here. And as I said, often these findings correlated with disease severity and at the individual level. I believe we use PPR in about at least a dozen patient populations, and it's still in use at the Martinos Center quite heavily. Of course, in the neurological disorders category, I need to mention dementia. We use PETMR in dementia to assess molecular anatomic functional changes. This was my second R1. Again, methodological developments, and then apply to AD and FTD. Jesse Fu working with Julie Price, they are currently looking at the tau and oxygen 15 water fusion imaging in 80 patients, and this is an example of looking at amyloid deposition as well in Down syndrome patients. Martinos, that radio tracer I mentioned, the first one that was developed at the Martinos Center. That's why it's called Martinos. It was the first one developed at the Martinos Center. There's nothing else about it. We used it for several psychiatric diseases. This is an example of using it to study schizophrenia, and the relative. This is I should have said it. It allows us to assess histone deacetylase expression. And we noticed that the relative HTAC expression is lower in the dorsolateral prefrontal cortex of patients with schizophrenia, and it was positively correlated with the cognitive performance across groups. Bipolar disorder patients showed lower MSTAT in several brain regions, and alcohol use disorders, they showed lower expression in the anterior cingulate cortex. So that was Martinos. And another example in psychiatric diseases comes from Mark Eldayev, who's the neurology department at MGH, who used PETMR to assess functional and metabolic changes after TMS in major depressive disorders. In the interest of time, I won't go into this, but the idea is we did TMS. We brought the TMS actually in the injection room, and we did it during the uptake phase and before and after. Interesting study. I don't think it was published, so I don't want to point more detail about that. Now, PETMR is an amazing tool for neuroscience applications. And this first group of studies, we investigated the relationship between metabolic changes and neurotransmitter signaling and functional connectivity. This project on the left, we studied anesthesia-induced unconsciousness and recovery using an alpha-2 agonist. This is one. It was quite a difficult study if you think about why do we simultaneous acquisition. And many of the examples I'm giving today fall in this category where you really have to capture the two, the PET and MR data at the same time. In this case, we were sedating, we were anesthetizing the patients inside the scan. That we had to have two anesthesiologists in the room just to be able to do something like this. And again, you want to look at both MR and PET at the same time. The second example was a study led by Josh Rothman from the psychiatry department, where we looked at we studied working memory, again, of relevance to schizophrenia. I won't go into details. And the last example, we looked at dopamine. We noticed dopamine, that dopamine, the medial amygdala network, mediates human bonding. Again, a very difficult study to do because it required us to scan mothers who have small babies. We were actually going to their homes, recording their baby playing, and then during the PET-MR scan, we were showing either a movie of their own baby playing or another controlled baby. So quite an involved study that we did. Simultaneous pattern MRI really shines when used to study neurotransmitter systems. This is an example of studies investigating the dopaminergic system. It's, I think, one of the coolest studies that was ever performed using pattern MRI that really shows the benefit of acquiring the data simultaneously. Again, it was a non-human primate study where we studied the neurovascular coupling to D2, D3 dopamine receptor occupancy. Now use the reclopride, cold reclopride to kind of displace the intrinsic study. And the top part shows the spatial correspondence between the MR, the co-localization between the PET MR signals, and on the lower part you can see the temporal correspondence and how we use this data to extract more information to test the classical receptor occupancy model, and then further study that Kristin Sandler performed over the years to go into more details and look into receptor internalization and other things. The second example is in humans, but in this case, we're studying the opioidergic system. So the response, looking at the PET and MR signal changes in response to pain, it's just cuff pain. Don't think we're torturing the patients inside the scanner. It was just cuff pain, but this was an example of that. And then the last one was again an example of a non-human primate study where we looked at the serotoninergic system and we looked at the response to the agonist and antagonists in this case. Also using one of our PET MR scanners, Jacob Hooper's group developed this novel approach called functional PET. So it turns out that if FDG is administered as an infusion instead of a bolus, so it can infusion from the beginning of the acquisition, it can be used to measure dynamic changes in glucose utilization in response to stimuli or tasks, and they call this approach functional PET. So if you look at this plot, you see the signal in two regions, the cortex with red, and then the frontal cortex, where you wouldn't expect any changes in response to a visual stimuli. And you see these small deflections. It's not easy to see. I'm not saying it's easy. It's not even easy to analyze this data. But if you use if you carefully look at the data and if you use all sorts of things to extract this small deflections, you can see it here. And this approach was used by others, not just the Martinos Center, to kind of perform similar type of studies and try to push the limits of what you can, the temporal resolution that you can achieve using this modality. The Martinos Center, Jing Chen, she's been using this approach to study sleep. So in this case, she's not just doing PET and MRI. She also, just to make it more complicated, she's also doing EEG in the same time. So it's a PET MRI EEG study, and again, the goal is to study the changes in hemodynamics and metabolic dynamics across wakefulness and sleep. I think she just submitted this. So I have a lot of slides that's unpublished data. So yes, we'll see how that goes. Now, this study and this study's Jingguan study, the other one, the previous ones I showed you on the previous slides, they really push the limits of what the current technology can do. And it highlights the need to develop, to have an imaging modality with higher temporal resolution. So this is an unmet need in the field that no technique currently used in human allows imaging of the dynamics of neurotransmitter function on the time frames that are similar to the time frames used for imaging hemodynamics using fMRI. And that is because the temporal resolution of our PET measurements is at least 1 order of magnitude worse than that of fMRI, as summarized in this table from Ciprian Catana and Sven Hesse's review. So if you think about, again, theory, going back to the physics, temporal resolution relates to signal to noise, and in fact, that is proportional to the sensitivity of the scanner. And this is the formula for the sensitivity of a PET scanner. And there are 3 factors. The first 2 are really related to the camera. The third one that it's not. Well, I guess you address it in a way by looking at the brain, which is a smaller object. It's the attenuation. The third factor is the attenuation in the subject. By using brain instead of body, you have less attenuation. But I will focus on the first 2. The first 2 relates to the metric efficiency. So how much of your, how many of the photons that are emitted you detect your detectors. And the second one relates to the detection efficiency. So once you have a 511 photon, 511 kV photons written on your detector, you want to turn that into a useful signal. So that's, again, solid angle coverage, geometric efficiency, and detection efficiency. Funded by the Brain Initiative, we are currently building a scanner with an order of magnitude higher sensitivity. And our approach to address the 2 main factors that I mentioned, the geometric efficiency and the detection efficiency, is shown here. First, to maximize the geometric efficiency, we moved away from the typical cylindrical geometry for a PET scanner to a spherical geometry. If you think about a sphere is a perfect scanner, right? If you have a complete sphere, you completely surround your subject with detectors. You maximize the probability of the photons to interact with the detector. Well, obviously, we cannot have a reasonably sized sphere. So we have some openings to allow the head to go in and some opening in the back to allow some cables to come out. But other than that, using this geometry gives us a 70% solid angle coverage. In terms of detection efficiency, we use high performance detectors with the depth of interaction and time of flight capabilities that gives us, when it comes to detection efficiency, when the stopping power, for example, for the crystal length we chose for the scanner, it's 90%. So in the end, when we put all this together, we get to a scanner that just from the hardware perspective gets us to a sensitivity of 25%. And in this table, I'm showing you the performance of the other 3 scanners I mentioned earlier. And here you notice that I listed 50. I didn't list 25. The other factor of 2 comes from this so-called time of flight sensitivity amplifier effect. It's listed here for the GE scanner as well. This is how, I don't remember which paper it is, but it's in one of the papers where they talked about the performance of the GE PET-MR scanner. They talked about this time of flight sensitivity amplifier effect. So using the same factor of 2, we get to 50. So this is what sensitivity we expect to have with the scanner. And of course, to make it more challenging, we designed the scanner to be 7 Tesla MR compatible. And that is because several MR techniques benefit from the increase in SNR provided by the 7 Tesla field versus the 3 Tesla field. And some may also benefit from the supralinear increase in contrast to noise ratio, and some representative images from data acquired with the scanners, the Martinos Center, are shown here. So where are we with the development? You see here the quite detailed drawing of the scanner, but so this is a drawing. This is the CAD drawing over time. Continue to evolve, and we update it many times, but the other pictures, most of them are actually pictures. They're not drawings. They are the parts of the scanner that we assembled already. So there will be 872 of this crystal arrays placed around the sphere. Those will make up the sphere. Although it's a sphere, we build it in rings. So What you see here is one of the central rings, and we have 19 rings in the axial direction. And these are some of the boards, some of them located in the bore of the scanner, right behind the sphere, and some will connect with optical fibers to other boards located in the control room. So in terms of the developments, you see here all the components that make up one ring. Here is the final thing. Actually, between the time when this picture was taken, the one on the left and the one on the right, we switched from machining this support structures to 3D printing. That was not a capability available when we started the project. Now it's amazing that you can actually 3D print such a large structure, and you see here the final assembled ring zero. Michele Scipioni and a postdoc in my lab, and Elena Allen, who's a graduate student, are leading this effort. We also build a 16-channel transmit receive array. Because of the space, you cannot. I didn't go in. You might think my talk was technical, but believe me, I could have made it much worse. So, in general, when it comes to integrated PET-MR, brain PET scanner, for example, you needed to have the transmit coil inside the brain PET, because the brain PET acts as a shield. It has all the detectors with copper, and you cannot use the body coil. So you need to build the transmit coil inside the brain PET, and then the receive coil inside the transmit coil. In this case, inside the sphere, we didn't have enough space to have two separate coils, transmit and receive coils. And because of that, we combine the functionality into the same element. So it's a transmit receive coil. So this was built by ASMA, working in Larry Wald's group. And it was, what you see here is actually images those are the first images they acquired after they built the coil. So where are we with the development? This is a kind of an updating drawing, but on the right side, you see the scanner, you see 11 rings assembled. In the meantime, we have 13, and we actually have the support structures for all the rings, but we are still waiting for the crystal arrays for the last, I don't remember the number. I want to say 64, but I might be wrong. 64 arrays to really put together the whole thing. So I'm hoping in the next few months, I keep saying that. I think Eugenie heard me saying this a few times, but it's really coming together. Now, this picture was taken in December. What you don't see is all the cables that connect the boards located here to the boards located here. So it gets a lot more scary looking when you put all the cables in place, but they will all be covered with the carbon fiber tube that we are currently manufacturing. And obviously the patient won't be seeing this. So in terms of our planned proof of concepts that are supposed to be performed, we're supposed to start doing this later this year. We proposed, it was aim 3.1 of the grant, to demonstrate the spatial temporal resolution of the high spatial temporal resolution. That's why it's called HSTR, high spatial temporal resolution brain PET, using controlled visual stimuli. If you remember the FPET study that I mentioned earlier, it's kind of the same idea. It's just that we'll try to push the limit in terms of the temporal resolution, and it will also allow us to look at spatial resolution by looking at the different layers as by MRI. In the second set of studies will characterize resting state changes in glucose metabolism and the relationship to hemodynamic changes across the whole brain. This is just an image where we try to push the limits using the current brain PET scanner, and it was very hard to get anything meaningful from this data. And in the third proof of concept study, we plan to explore the dynamics of dopamine receptor signaling adaptation using repeated bursts of microdose pharmacological challenges. Very excited about the studies. And again, that may be for 2 years from now I come back. So in terms of kind of a more general view of beyond the proof of concept studies, what are the novel imaging capabilities and potential benefits of using such a high sensitivity or high temporal resolution scanner? Well, I mentioned the high temporal resolution already, but you can trade off the improved SNR in various ways. You can, obviously you have high SNR images, you have much better quality images, or you can perform very fast static imaging, or you can take advantage of the higher sensitivity to image much later, three half-lives later for all radio tracers, and so on, improve quantification. And when you have such high sensitivity, you can also try to really push the limits of spatial resolution as well. That's one of the challenges. Now you can build a scanner that has very tiny, small crystals. The reality is you won't have enough counts to actually get good quality images if you don't have the sensitivity to support them. Now, going even beyond that, how will the neuroscientists use the novel imaging capabilities of the scanner? Well, to quote famous physicists, it is very difficult to predict, especially the future. And looking in the crystal ball made of scintillator arrays, I see this scanner enabling several more advanced applications, such as the ability to track brain-wide dynamic changes in neurochemical processes, to study the dynamic interactions between functional and neurochemical connectums in neuropsychiatric illnesses, or to investigate the dynamics of neuromodulation of different time scales. Even further in the future, I see the possibility of generating virtual brain twins by integrating connectomics data using AI. As you could see, I didn't talk about AI almost at all, although, as you know, AI is impacting our lives in so many ways. But even when we wrote the grant on purpose, I think I added a paragraph towards the end of the grant, and I said, we want to build the best scanner we can before we add AI, right? The best technology. And then obviously, if you combine that with AI, so this is a big project to accomplish all the aims. We have assembled 4 teams of experts from 8 institutions around the world. We have these 4 teams: PET hardware, PET software, systems integration, and neuroscience. And I'm convinced that together we'll be able to turn on this light bulb needed to measure the neurochemical dynamics. So I won't stop here. I have so I talked about PET-MR until now. Now, as you are aware, perhaps one of the most important technological advances in the PET field was the development of total body PET CT scanners. And as you can see from these drawings, the scanners provide substantially higher body coverage, which results in a dramatic boost in sensitivity. If you think again about the solid angle coverage I mentioned, sphere is one thing. A long cylinder is another way to maximize the solid angle coverage. And this is the Simon Cherry and Ramsey Badawi at UC Davis. They built together with United the U Explorer. It's a scanner with a 194% field of view, axial field of view, and several dozens of these scanners are installed around the world. 2 such scanners are commercially available. United introduced their 2nd generation, Panorama GS, and Siemens introduced their BioVision Quad. And the first images obtained with the scanners were stunning. They, in addition to the stunning images, they also allow for multi-organ dynamic imaging, as you can see in these examples. So in the never give up on what you really want to do. Some years ago, I got very excited about this novel imaging modality and said, we need one of the scanners at the Martinos Center. Usually joke that we have everything. Well, we didn't have a total body PET CT scanner. So I started to submit shared instrumentation grants to try to get funding for such a scanner. So I had several attempts, and I'm going to tell you about my attempts. First attempt was I submitted the proposal in June 2020. It was not funded. Obviously, there were many more comments from the reviewers. Some are here. They complain about the fact that most of the projects were neuro-focused, which shouldn't surprise you after everything I talked about today about neuro. But sure, Martinos Center is primarily neuro-focused. Those are the studies that were funded. Those are the studies I highlighted. Maybe that was a mistake. Anyway, I fixed that later on. I'll tell you in a second. The other comment I got was that the user fees are $650 an hour, which makes them prohibitively high. I thought that was really outrageous. Now, for a scanner that costs $9 million, you're saying that 650 an hour, it's prohibitively high. Anyway, I didn't give up. So the second attempt came with more pearls of wisdom from the reviewers. Maybe I kind of agree with the first one, although I did my best to really show how the new scanners, this total body scanner, would enhance the projects, not just expand their research scope, which is challenging. You know, when those projects were funded, there was no such scanner commercially available. So it's not like you were not funded to use such a scanner. But the thing that really upset me when I read that in the summary statement was chicken and egg problem. This is a chicken and egg problem. I'm a reviewer myself. I would never say it's a chicken and egg problem. How would I solve it? How can anybody solve the chicken and egg problem? It should not end up in a summary statement for sure. So third attempt, June 2020. Finally, now I pretty much replaced all the neuro projects. I addressed the reviewer concerns, and we got the shared instrumentation grant to buy this scanner. Well, I just mentioned the price, $2 million doesn't take us too far. So never give up. Obviously, I couldn't get another shared instrumentation grant, but Mass Life Sciences, they have this research infrastructure program, and I submitted an application, and I managed to get even more money from MLSC. So we are trying to talk about unpublished data. Now I'm going to talk about future. We are trying to establish the total body density MGB program. I'll tell you in a second why MGB. By now, you might be convinced that I'm extremely biased. Everything I showed you was done with Siemens scanners. And I guess if I were to ask you now, which scanner do you think we bought, the United Panorama GS or the Siemens one, for sure you'd say the Siemens one. Well, it turns out that no, we'll buy the United scanner. And that will be a surprise for many people across the country, across the world. The order was placed few weeks ago, the PO was issued. It was a long process to get us here. No, it's not like it happened overnight that we decided to buy the United Imaging scanner, but that's what we'll do. We'll have a United Panorama GS scanner installed at the Martinos Center. I'll tell you in a second timeline. But in addition, now the money we got from NIH, from MLSC, we managed to convince this institution of the great potential of this technology. So we got more support. One thing I didn't mention was that Brigham, you're also talking with Siemens United about maybe installing a total body scanner. So we joined forces and we had those conversations as a team. And in the end, we'll not install just one scanner, we'll install two Panorama GSs, one at the Martinos Center and one at Brigham. The title that Jimmy mentioned when she introduced me, the Director of Collaborative Research and Innovation. That's actually at Brigham, not at the Martinos. So I have another title at Brigham, and that is to support this bi-directional integration and translation and research and clinical care. So we'll move forward with this in three phases. Phase one, it's the scanner being installed in Martinos Center. You see bay 5.5, which is kind of unusual. I mentioned the 8 bays, 1 to 8. Well, we created another bay. We turned the space we had for one of our old 7 Tesla scanner that require extra shielding and so on. And we turned that room into a 3 Tesla room. And we took some of the space and the equipment room. And that's what you see here on this floor plan. This is the space for the Panorama GS. So there will be a 3T here and there are offices here, but we managed to squeeze a scanner in that space. The timeline for this, if everything goes well, is end of June. By end of June, I would like to have the scanner installed. I mentioned the research projects that support this proposal. These are the PIs and the titles of the major minor users. And as I said, I had to switch from brain to body for most of the major users. We kept a lot of brain in as minor users because I know the scanners are useful for brain, or they will be extremely useful for brain as well. And I mentioned the novel imaging capabilities in the context of the 7T brain PET scanner. That applies here. There are small differences in all the capability of doing CT imaging. This is not something we can currently do at the Martinos Center. Talking about things we don't have. We don't have a CT scanner or PET CT scanner. This will be the first CT scanner as well at the Martinos Center. So I summarized in this table all how the different imaging capabilities will benefit different projects, or if you want to think of the other way around, how different projects will be enhanced by this novel imaging capabilities. And the plan in phase 1 is to implement all these capabilities for the radio tracers that are currently used at the Martinos Center, and we'll use this paradigm of develop, validate, apply. I use this a lot in my grants: develop, validate, apply, and refine based on the findings of those studies, and apply not just to brain but to other organs. So this is a way, in a way, this is our plan for supporting those studies that supported the proposal. In phase 2, in the bidirectional integration of translational research and clinical care, it's kind of the same model. It's just that here I'm not talking about novel imaging capabilities, but it's the desired, let's say, imaging capabilities in a clinical setting. So I always like to start with improve image quality. I think in my mind, I think that's the most important. But I know leadership, they also care about throughput. So that's number 2 there. We'll develop workflows for maximizing throughput with the scanner. And the concept is similar: develop, validate, apply. It's just that now we have two ways of doing that. One is go directly through the develop, validate, apply for clinical care, and then refine. But there is also a path for this bi-directional communication between translational research and clinical care. The other thing that's different on this slide as opposed to the previous slide is that the tracers that I'm listing here as the tracers currently used at Brigham for clinical purposes. Most of them FDA approved as opposed to the previous slide. Good. And in phase 3, once we have all this in place, we can move forward with this dream I have of being able to use the scanners to study interconnected systems. This is actually the story I wrote for getting the MLSE proposal for funding. And I don't think I will wait for this really to be phase 3 5 years from now. I think I will probably later this year will start to work in this direction, because I'm very excited about the possibility of beginning to really integrate, study brain in relationship with the body. That be, brain heart, brain gut, and so on. So I think there is a lot of things we could do in that area with the scanners. And of course, I didn't talk about radiochemistry developments. I didn't talk about AI, but the dream is really to be able to integrate all these latest developments in radiochemistry, and in software I include AI in the to study the human body in novel ways. So to take you back to that one of the first slides where I showed you the scanners installed at the Martinos Center when I joined, that changed quite dramatically. I would say for most of my time with the Martinos Center, we had 8 bays with the 2 PET-MR scanners. And now this will change into 4 bays that will have PET capabilities. One will be PET-CT, which is again first for Martinos Center. I can take you one by one. Bay 2 is this 7. We upgraded our 7 Tesla. We have a Terra X. We'll upgrade the old, the classical, one of the prototype 7 Tesla scanners that we had for many years. That will turn into the Terra X with an advanced gradient. Bay 5.5 I mentioned, the Panorama GS. In basics, we'll replace the old brain PET prototype finally with a newer scanner developed. We were at the Martinos Center the other day doing measurements for a planned installation. It's March, April. And then in day 7, that's the PET MR, the biograph MR. Siemens recently announced their second generation MMR. They call it biograph 1. Going to comment. But I just submitted an MLSE proposal to hopefully get funding for upgrading the scanner. So that's how I see the near future for Martinos Center in terms of equipment, and kind of everything starts all over when it comes to methodological developments, needs to address challenges, taking advantage of opportunities. Kind of the same model that I see applied to PET-CT or to the 70 brain PET scan. So to conclude, I like to think of simultaneous PET MR as the holy grail of neuroimaging. We have used this modality for numerous research and clinical applications. The ability to correlate the measured signals, temporally correlate the measured, spatially correlate the measured signals, has allowed us to study the brain in novel ways. And I'm very excited about the future in terms of the high sensitivity PET scanners that will lead to new advancements in molecular applications. I will end with my long acknowledgement slides. I'll take any questions you might have.
That is really amazing. So much more content. Anybody has any questions? Nuclear medicine. Anybody? Well,
There has to be something that you like, at least one slide.
But it was great to hear that you had submitted a grant and got the rejected. Like, wow, feels like when you're seeing somebody who had extremely successful, you feel like you're, always like getting acceptance. But I think that there's so many rejection before getting a success. So that's something that we have to remind ourselves that, we tend to kind of give up. But
absolutely, I have a similar slide for the 70 brain PET. That took even more attempts to get funding in different ways. In the end, fortunately, the brain initiative funded happened, and that allowed us to get that funding. But it was hard to get funding for that project.
Yeah. $650 an hour is pretty normal, right?
Yeah,
I mean, we charge you $650, don't we?
Well, it depends. That depends.
For 3T MRI.
Yeah, that's a lot. You get a lot more from.
Yeah,
Yeah.
Exactly.
No, that's I don't know. Actually, when I resubmitted the grant, I reached out to friends across the country to see if it's really outrageous, and all the rates were much higher,
My
including
mechanic charges that.
The psychiatry disease is something that we haven't explored in a brain imaging. I think a lot of them it's kind of good comparison of schizophrenia versus control, or autism versus normally developed children. Is it really the imaging technology robust enough, sensitive enough to really make a diagnosis at the individual patient level, or not quite?
Well, the answer is imaging, PET imaging used in psychiatry? Almost not at all. So is that the robustness of the technology? I don't know. I don't think it's the technology itself. Don't we have the right radio tracers? I don't know. It depends on the questions. We have. I showed several interesting examples, but the reality is clinically, we're not there yet. Yes.
I was a MGH resident many years ago, but went in the wrong door into psychiatry rather than neurology. So I am hearing your comments with big interest. In the time that we've been here, Debbie and I left Boston 15 years ago, there's been a huge acceptance growing over time that says psychiatric illnesses are terribly important to understand. And in fact, the one that we've tumbled on to study is suicide. That will be the psychiatric illness of the next 5 years in our state. And it's really important because you think that you're at sea level now and you're safe. But starting about 2,000 feet, as you go up in altitude, you get this increase in suicide rates by about 35%. So it's a big problem. The state cares about it. It affects our kids, which is why the state cares about it. You might want to think about this as you plan your next 5 years.
Yeah, I used to have a slide many years ago where I was talking about the global burden of neuropsychiatric disease, which is much higher than everything else, really. And we still don't do enough when it comes to
Yeah.
using imaging for this.
Yeah.
I agree. I don't think we have anybody looking at that right now, but I can see ways of,
Well, the back pain things was interesting, Dr. Hutchins. You treat the patient with the back pain. But it's you can see there's a pain, not just the local pain, but the what pain is perceived in the brain.
Yeah.
And then that
Correct.
seems to be a quite exciting tool to see somebody's faking versus somebody's really hurt. In a way that you can actually see the
and if you're
response
interested
to
in
the
that,
pain.
Marco Loggia, please invite him. I don't know if he's his, but please invite him and he will give a.
Man,
She will tell you more about
screening for all
he's doing
residents
a lot.
next year.
Yes, please.
Why did we,
Ones that are
did you choose the United, just because both of these scanners are amazing clinically, I think. Did you choose United over Siemens in the end? Was it, other than maybe they gave you a deal?
It's funny. So if you compare the two scanners performance characteristics, the GS is superior in every way, sorry.
Okay.
From a financial point of view, it was also, let's say, similar.
No, clinically, you can do a lot more.
So you basically get a better scanner for the same price.
Yeah, you can do a lot more patients with that type of scanner.
Yeah, and you have a longer field of view. Yeah, it will surprise many people. I think you are the first, audience that hears about this. There will be a press release at some point. I approve the press release. It will be reviewed by the MGH Public Affairs and it will take probably another month. But it will surprise many people that Martinos Center installs United. It will shock many people. Obviously, Siemens knows. We had these discussions. We talked to them. They know about our decision. So it's not like I'm telling you something they don't know already, but that's a reality.
I visited UC Davis before pandemics, but the whole body dynamic PET scan, oh my God, breathtaking. To see that picture, that injecting go to the heart and go to the lung and the body, the outflow to the brain. It's just incredible, and it's super, super high resolution.
temporal resolution.
The
too.
temporal
It's
resolution,
amazing.
the
It
bed
really
doesn't move.
changes.
You get a whole body just simultaneously firing. And then the resolution, the things that we never seen before, it's just incredible. So I know I saw the Simon Cherry is your PhD advisor.
Yes.
So
Smart guy.
Yeah, maybe that helped as well. I don't know without decision.
Well, one thing though, I really think it's really important to look at that, not just the neurons or bodies or heart, but really interaction between those organs. So you mentioned toward the end, brain, heart, or gut, and heart, or all of the connection of the human body, because it's really affecting in many different ways. And I think that might be a really the future direction.
Yeah,
is a
I'm
connection.
very excited about it. I couldn't tell you I already have a plan for me, it's always grants, right? I live on soft money, to send me grants to get either the toys we have or the projects we have. So I don't have yet the aims for that, but
That's a coming. I think this is something that we are
Yes.
very interested in, is
Yes.
the brain, heart, or gut, brain, or gut, heart, all of those things to how interacting with each other. And in dynamic PET scan probably will show a lot.
the challenge I can tell you is, and that's probably the reason I don't have a scanner yet, so it doesn't make sense to submit a grant just yet, but I could submit one in June. The challenge is that the thing I will struggle or work on until we get to that grant is which radio tracers do you use for looking across the body,
Nice.
right? FDG is one example where sure it might be relevant in the brain and in the body, but you need to, it reminds me of the question I used to get in terms of the PET-MR. Why do you need simultaneously acquired data? Now this changes in why do you need to simultaneously image the brain and the heart or the gut,
Yeah.
and which radio tracers can you use for doing that? There are no good answers.
Yeah.
I don't have yet good answers to that, but I will have to come up with good answers.
I see. Right. Any other question?
May I ask a question?
Yes, oh,
Okay.
sure, yes.
Oh, hi, this is Eun Park in nuclear medicine. Thanks for a wonderful, inspiring talk. I'm so impressed. I was actually working and listening, so please correct me if I'm wrong. So would you tell me more about the ultimate path for dynamic in vivo brain imaging? So does it enable real-time monitoring of receptor binding changes or neurotransmitter concentration changes with a, for example?
So, well, you asked several things. Real time, it won't be real time in general, but we
Yeah.
don't develop software to look at real time, although there is a way to process the data in real time and actually look at that in real time. We don't have such tools. We might implement them for the scanner. But I think the more important question is not just real time, but the temporal resolution. Are we going to really be able to have the temporal resolution, even if with this scanner, to look at the changes on the second range?
Right.
I don't know. I don't know yet. Maybe for very, I don't know. If you have something where, in the end, it's signal to noise, right? You need to have a relatively large region where you have those changes. So in the end, your signal to noise is sufficiently high to push the temporal resolution limit. I don't know if we'll be there. I'm hoping we'll get it to the. Let's see. Should I say tenths of seconds or seconds? That's what I'm aiming. That's what I'm aiming. I think we'll get to tenths of seconds. And it depends. Do you want to look at voxel-wise across the whole brain? You won't be able to do that with 1 second temporal resolution. I mean, you will, but you won't be able to look at fluctuations on a voxel with that temporal resolution. But if you have processes where you average across multiple voxels, it's a trade-off that you'll have to play. It's hard to give a general answer to that question. I think it will be very specific to the application related to and so on.
Great. Well, thank you so much. You really
Like,
There's no need the second time.
Please speak.
Make the one
Oh, wait, you know where the room is?
Well, no, we can't make the 115 screen.
I'm knowing.
I think so. I didn't get it.
I have read.
The bread department?
It's not inside, outside.
I did get it, yeah. I think it's just like.
I'm trying to find a physics cheat sheet and see if there's just a shortened version I can do on MRI. So I found the ACR one and it was like, here's a couple of like practice physics questions. And you can also which covered stuff I had read.
But I'm over here. I mean.
I know.
Actually. Department upstairs, I think. I think there's gonna be a bunch of those left. Oh, yeah. She was on camera. We just switched it. You're like looking at the panel screen. I know that'd be cool. Yes, I had a doctor. Because flu is treatment. Yeah. All that backwards off. Had a doctor. Yeah, he just. I couldn't remember. Like, well, maybe it doesn't matter. Yeah. Or no, no, it's me. Yes. That's how to get it close. So if you're, but I'm not. Yeah. Just give me something that's like in this. Oh, I get mine both. I just. This makes me really appreciate my chart. Yes, because it's kind of. That's the blue shot going away. It is such a big, yes.
I can form a
Second floor makes all you.
But I have to buy it.
It's right across.
Donna, do you think you can take
Okay.
it to the second floor Magnolia?
I mean,
Yeah, if I can find it. I think I know where it is.
Yeah.
oh,
They're gonna be
yeah,
fine.
but you're
Yeah.
gonna-
I have to find a, I
Yeah,
have
we'll
to find
find
a
it
water.
together.
And this one did not get great water filtration. Yeah, that was a lot of fun. It really neat. I'm really curious because it was great that you oriented us on.
Cyprian, do you,
Yeah, so-
sorry, do
yeah.
you wanna eat those or do you wanna have a mix? There's a.
I don't, I thought we have, don't we
Yeah,
have lunch?
yeah,
I don't know, I
lunch,
can't find my.
So,
You
either way, so you gotta have a food in the.
Yeah, it's spread out